Hello everyone, this is Gemma Roig, and I'm gonna talk about measuring representation similarities of task-specific vision deep neural network models for transferring learning and incremental multitask learning. And before I start, I would like to thank the organizers of the Continual Learning workshop for inviting me, and it's a pleasure to give this talk to all of you, and I hope we can interact later during the panel discussion. So before I start, I would like to give a little bit of background and motivation. So DNNs have really taken off in object classification, and object classification is mainly the task of answering what is in a particular image or what object is in there. And what you see here are some examples of the ImageNet dataset. And here I'm just showing you some DNN architectures, going from the first one that really was the pioneering one before this DNN fever started, let's say it in this way, in 2012, which we call AlexNet, and then how this architecture evolved with deeper layers and wider and skip connections in the case of ResNet to have more and more accuracy in this particular task of object classification. So here what you see is that before the DNNs, we had an error rate of about 0.3. In 2012 was when AlexNet won the competition, and you can see here the difference in error rates between the models that didn't use DNNs and AlexNet, which is quite a margin. And since then, all the models that have been used in this competition, which is no longer sustained as a challenge, but still we have the data set available, has been all based on DNNs. And here I just wanted to see with some of the names that most of you are familiar, and then even in 2014-15 it was claimed that DNNs could perform better than even humans. And the story doesn't end here, because the success of these networks have been so wide that it has transferred to another scientific domain, in this case neuroscience, in which these neural networks have been used to explain brain data and activations of neural responses in the visual cortex. And this now it's an area that it's very broadly explored. And as an example, I want to talk very briefly about this challenge, in which we call the Algonauts project, which consists of explaining the human visual brain using models, and in particular, most of the models that are used in the challenge are, of course, deep neural networks. And this was a challenge that we had last year, and it was for object classification. So we had brain data in which humans were looking at objects, and then the neural activations were recorded with fMRI and MEG. But what I want to put emphasis is that we need to go beyond object recognition, and I guess most of you will agree. And one way to do that is to start by studying the relation among tasks. So for this, we can build, for instance, a task taxonomy, and we can apply it in transfer learning, but not only that, and we can also use this study of relations to build a multitask model. So to have a shared core model, which can have task modulated parameters or even functional blocks for each task, inspired by how the brain have different regions of interest to perform different tasks, but overall the brain, it's only one huge network. And then, of course, since I'm also interested in how we can use these models to explain brain data, then we can also explore how we can leverage these new models that go beyond object recognition to also explain the specific brain regions. So I will start by talking about this project, which was mainly done by my PhD student, Shitish Duality, and was published at CVPR last year. So what we wanted to study is the relation among tasks to build a task economy, and then in the application of transferred learning. So here the question would be, how are different vision tasks, in this particular case vision, we studied, but it could later be extended to other modalities. So how are these related? So what we did to study the relation among tasks and building a task taxonomy, so we leveraged of a method. So we proposed a framework in which we compute similarities among representations between these different tasks, taking a subset of some images, so input stimuli, compute the representations of the different models that have been trained in different tasks, and then call what is called representation similarity analysis between all these tasks to then be able to obtain this matrix that you see here on the right, which is the task similarity matrix. So here it's 20 by 20 because we use 20 tasks from task taxonomy dataset. So as I said, the relation among tasks, for building the task taxonomy, we use what is called representation similarity analysis. So this is a method that is widely used in neuroscience for comparing brain data and models, or behavior and models, and behavior in models and brain data. And what we do is use it to compute relations between different models. So how can we get these similarity scores for two tasks? So first we need to compute a representation dissimilarity matrix for each model with pairwise dissimilarity, which is 1 minus the Pearson's correlation. So here you have, for one model, you have a pair of images that you compute the representation that you can get from a particular layer, the output of a particular layer. Then you compute this dissimilarity between the pairs of representations or feature activations, and each of these pairwise dissimilarities will be an entry in this matrix. So at the end of the day, your matrix will be a square matrix of size square the number of images that you are using. So when you have these dissimilarity matrices for a couple of models, then you can get the similarity score for two models that perform different tasks. So one could be, for instance, object classification, and another could be semantic segmentation, just to put an example. And this is quite relevant because using these RDMs, the representational dissimilarity matrices, allows to compute dissimilarity scores even if in the two different models we have vectors that are of different size. And the intuition behind this method is that if in one space, if in one model, two stimuli are as dissimilar or as similar as in the other model, then the representation similarity is very high. So what we do is we take a taxonomy dataset, which was introduced by a lab in Stanford, that contains several indoor scenes with annotations of different visual tasks, like, for instance, colorization, edge 3D, norm calculation, semantic segmentation, etc. And with the RSA approach, we compute this task similarity matrix, taking all these different tasks. So we have models trained on different tasks, and then we get the activations at the encoder for a subset of the images, and in this case we only use 500. We do an analysis and 500 is good enough, so it's very fast to compute this matrix. And we have this task similarity matrix, which what we can see here is that if we do a hierarchical clustering, and we colored here 2D models in blue, 3D models in green, semantic models in magenta, and geometric models in red, we can see that the clustering with this method, really we get a group task into these meaningful clusters of 2D, 3D, semantic, and geometric. We also study what's the dependency of this method with the model size and the dataset size. So we use, in the previous slide, this matrix was obtained by taking full models trained with all the training set. But what happens if we train smaller models to compare to the larger models? Because here, really, we don't need to have state-of-the-art accuracy to find the similarities, but only to get a ranking. So if by taking smaller models to compare to the larger models, we get the same ranking, then we could leverage this approach to use it maybe for transfer learning, which we will try next. Because in transfer learning, we have less number of images, and also we have to have models that are smaller, because otherwise test them, we wouldn't have something that is meaningful. Maybe they would be overfitted. And what we found is that actually the ranking is quite preserved. So that is good news. And also, if we change the number of images, when we get up to 500, as I said before, this is pretty stable. So this ranking doesn't change, which is also quite good. So what we did next is to try and build this framework for transfer learning. So now we have a set of models, and nowadays that there are so many models online, why do we always need to start to do transfer learning from a model trained on ImageNet? We could just try many of them, but which one? So that's what we built, a framework for deciding which model to pick to initialize the model to do transfer learning on. And we do this model selection using the RSA approach. So here we can see how we do that. So we build a small model for the new domain. In this case, we use Pascal VOC semantic segmentation. And then we build this model with a training set. We get a subset of the validation set or the task set. And we compare to all the taxonomy models, the big ones, to have the ranking. And here you can see the ranking that we obtain when we compute the similarity score between the small new model trained on Pascal VOC semantic segmentation and all the available taxonomy models. So here what we can see, which is quite nice, I think, is that the highest model is not the one that is of semantic segmentation. And we thought about it, and here the insight is that actually the domain of Pascal VOC semantic segmentation and taxonomy is quite different. And the one that is chosen here is object classification as the highest that we should do transfer learning for. And here what you see is actually when you do fine-tuning to the new task, taking each of the models, you do have the same tendency as the ranking with the RSA. And here more quantitatively, what you see is that when you take actually object classification, which was the one selected by our framework, does give a higher accuracy when you do transfer learning from this than of semantic segmentation. But as you saw before, so this ranking and the tendency of the accuracy is not perfect. So we continue to explore this work and see how we can improve this similarity measure in order to have a higher correlation between the rankings of the scores and the actual transfer learning accuracy. So what we found is that we can pose this as a duality diagram similarity and use this as a generic framework for initialization selection in transfer learning, in task transfer learning. And as I will see, RSA is just a particular case of this dual diagram similarity. So a duality diagram of a matrix X, or Y in the second row, is a triplet X, V, and Q, consisting of a matrix Q, which has a dimensionality of the number of features of the model that gives you the model. So it would be the number of feature outputs at a particular layer, for instance, that we choose. Which quantities dependencies between the individual feature dimensions, this matrix Q, and then the matrix D, which is number of images times number of images, assigns weights on the observations or the images. So to compare two duality diagrams, the one on the top row and the one on the bottom row, here that you see, so Robert and Escoffier introduced this RB coefficient. So the RB coefficient is a multivariate generalization of the square Pearson correlation coefficient, which is used in the RSA, this Pearson correlation coefficient. And then the motivation behind this RB coefficient was to map these n observations, so n images of X, which have D1 dimensions, and Y can have another dimensionality, for instance 2D. So then the similarity between X and Y can be assessed by comparing the pattern of obtained maps, which is comparing the set of distances between all pairwise observations of both maps, which are images in our case. And how we compare them is with also this kind of dissimilarity matrix, which is M, but it's built with a generic function F. And then the score is G, which can also be any function, similarity, a score function, to compare these dissimilarity matrices. So as I said before, this dual diagram similarity, it can be posed in RSA terms. So RSA is a particular case of DDS. And here you can find, so D is the identity matrix, Q is the centering matrix, F is the Pearson correlation, and G is the Spearman's correlation. We also can pose the VDS as the center kernel alignment. Here you can just see the equation of CKA for your reference. And how we can do this is making D the identity matrix, Q also identity matrix, F the linear or RBF kernel, so they use both for building these dissimilarity matrices, and G is the cosine distance between unbiased center dissimilarity matrices. So now that we can see that we can pose both RSA and CKA as these particular cases of DDS, so we can really explore other combinations of Qs and Ds and Fs and Gs that can lead to this higher task transfer learning. So maybe higher similarity leads to better transfer learning performance, which indeed is what we find. So what we do is we explore how we pose Q and D as particular instances to have identity matrix, Z scoring, batch normalization, instance normalization, layer normalization, group normalization. Okay, so with identity we will have the CKA and the RSA for particular cases of F and G. So here I don't have the derivations, we have them in the paper, which we will upload very soon. So as I said, now we have the question of which combination of these matrices Q and D and functions FG leads to higher task transfer learning. So we explore all these functions, and we here give the equivalence with RSA and CKA, so Pearson's, Euclidean, cosine, linear, Laplacian, and RBF. And G, for G we use the Pearson correlation in all cases, but we could explore others as well. So now how do we test that? So our experimental setup is very similar as before, so we use taxonomy models, and we also use the pre-trained models. And as the representation of each model, we use the output of the encoder. And here what we get is that actually the results, so when we use as F askew. The z-score is the one that leads to higher transfer learning performance. And actually also in F, to build the dissimilarity matrices, the best is to use nonlinear functions like the Laplacian or the cosine. And here what you see is in affinity and win rate, which are two measures of how well transfer learning performance is measured. So the measure of transfer learning performance goes together in these different previous state-of-the-art RSA, and also with our particular instances in DDS with F cosine and Laplacian. So we can see that we can get much more than state-of-the-art. So here you can say taxonomy win rate is 1, of course, because it's this measure, and with affinity is 1 because it's this measure. So we take this as gram truth, which has also been taken in the previous state-of-the-art words. So we also do this transfer learning performance with Pascal VOC semantic segmentation, and what we compare is how important is the set of images that we use to compute these dissimilarity matrices. And what we find is that it's very important that we use the images from the same data set that we want to transfer from. This is one. And again, the DDS with the Laplacian is the one that works best. And Z scoring, that's what we take. We also use this same setup, but now instead of doing model selection, we have another assumption. We have what if we have only one model and we want to do layer selection. So we can do exactly the same approach. And what we do is we take a ResNet pre-train on ImageNet, and we compute the similarity scores using taxonomy models, and we find that the output of the first block is more related to 2D tasks. The second is not so clear, so between 2D and 3D. The output of the 3D block of this pre-trained ResNet on ImageNet more to 3D task, and the fourth block is more related to semantic. And here we use Laplacian centered with Z-normalized features, which is what we found that works best in the previous setup. So how do we test this? So we take this pre-trained ResNet on ImageNet, and we branch out from these different either block 1, block 3, or block 4 to see if what gives a better transfer learning performance in these two different data sets, Pascal VOC and NYU. And indeed, we find when we do fine-tuning on all the different blocks, branching from all the different blocks, that what we found with this task similarity in the layers is what it works best. So we can also use this to think about going towards multitask model, having one core network that can be shared among all the tasks. So we think on this like having this core network with different functional blocks, one per task. And this would also allow to select from where to branch when we have a new branch. And it also allows to do this multitask learning in a continuous way, learning first one task and then learn another task, because the core network is shared and it doesn't change in one of the setups, and in another setup it's just modulated. So it doesn't affect the other tasks that have been already learned. So as I said, so here we use this determination of task dominance for each of the block, as we did for the block selection in the previous setup, as I said, using RSA in this particular case, but we could use the more advanced similarity approach. And at this point we know already what is RSA, so I will skip this. And not only we tested for ImageNet, but we also tested for places, so a model that's also a ResNet, but it's been trained on places and not on ImageNet, and we have very similar results. So first block more related to 2D, third block to 3D, and last block to semantic. And here what we do is we compute the transfer learning performance in 2D task, 3D task, and semantic task, in 3 different data sets. And here what we see is that actually when we do this branching out from the block that is more affine to the task that we are learning new, the transfer learning performance is better. And here in this case, we are fixing the network, the core network, and we are only learning the parameters of the decoder. But of course, one could think, why we have to fix the parameters of the core network? We could also modulate them according to the task that we want to predict at a particular time, or even if we want to do it parallel, we can modulate for each of them. And this is what is represented here. So one core network and then this modulation. So how do we have this modulation? So we use it with batch normalization parameters, and which are these two parameters here, the scaling and the shifting, which we learn them as task-specific parameters in the core network. And we also, with a modulation, with a parameterized ReLU, that is, we'll also learn it as a task-specific. So again, this allows to have a shared network that can incrementally add tasks, and the amount of parameters that are changed in the core network are very little. So here we measure it again in transfer learning performance with and without task-specific parameters, and again the ImageNet as the core network, pre-training encoder, and branch on 3 different tasks. And what we see again is that with the modulation we have better results than without modulation, of course, because it's more adapted to this task, but still with all this massive core network that is shared across all the tasks. And I would like to go back to one of my points of the beginning, that we also want to use these kind of models to explore the representation of the vision tasks in the brain. So if we have different models that are trained on different vision tasks, then we can use them to also understand the functionality of different brain regions. And hopefully, if we understand them, then we can go back and change our model and potentially build a better multitask model, which is the goal. And here just an overview. I won't go into details, just to say that the framework is very similar to the ones in which we were comparing 2 different models, but in this case one of the models is the brain. So to sum up, what I want to say is that I'm interested in going beyond object recognition or object classification. I have talked about multitask and multi-domain models, not multi-domain, but multitask. So one of the next steps is also to have multimodality, not only multi-domain, as we had presented here. And so these are models that have shared parameters and domain-specific parameters, each for domain or task. So here, one of the goals, of course, is to minimize the domain-specific parameters, but maximize the accuracy performance. And we can do also this in an incremental and lifelong learning manner, in which we can learn one or few classes at a time, or even different tasks, without forgetting what has been learned before. And then this has the potential in the future, which I haven't talked about, for few-shot learning, because the model has already a lot of knowledge, and it doesn't need so many data to adapt to a new task. So for this, hopefully, if we have this modular multitask model, it will be easy to overcome this catastrophic forgetting, and also with the help potentially later with the generative models and the synaptic weights. And finally, if we have such a model, we can see if we can explain better the brain responses and get back and improve the model again to kind of have this loop of interaction between neuroscience and computer science. And finally, I just want to mention that the Algonauts challenge that I mentioned at the beginning that we organized last year for object recognition, in which we provide brain data, and the challenge is about having models that explain this brain data will be extended, and there will be brain data collected while people were watching videos, which also make the models, it enables that people can use models much more complex in the sense of using the temporal domain and also other tasks and not only object classification. So with that, I would like to conclude my talk, and thank you very much. And I hope we can talk later. Bye.